This is Max Born. In the 1920s, Max Born laid the foundations for understanding the quantum world. Today, scientists put Born's principles to good use in so-called neutron scattering experiments. When physicists found out that Newton's classical mechanics were useless to describe the microscopic world of atoms, Born had a radically new idea. All elementary changes happen in quantized steps, the quantum transitions. And whether or not such a transition is going to happen is only governed by probability laws. Neutrons are great for demonstrating the principles of quantum mechanics because their interactions with matter are weak. A neutron scattering process typically involves only a single quantum transition. Tobias Schrader is a scientist at JCNS, the Jülich Centre for Neutron Science. JCNS uses the best neutron sources in the world to conduct experiments for a range of applications, from basic research to material science and medical studies. Dr. Schrader works at the FRM2 neutron source in Garching, near Munich. Let's have a look at a typical neutron scattering experiment to understand how Born's ideas come into play. Neutrons with a well-defined initial momentum p are bounced off or scattered by a crystal. They undergo a quantum transition to a final momentum p'. The scattered neutrons are recorded by a detector, a special neutron image plate camera in this case. Typically, after 1 hour, the first results are in and we can make a few principal observations. There's always a largely uniform background of neutrons scattered in all directions. We cannot predict where a particular neutron might end up, but a few specific directions seem to be preferred, leading to the formation of so-called Bragg Peaks. Usually, Bragg Peaks are explained using a wave analogy for the neutron particle and the interference of these waves. But that is in fact not necessary. We can treat each neutron as a particle and still get our peaks. As we've seen before, a neutron hits the crystal with momentum p and bounces off with momentum p'. One condition for Bragg scattering is that the neutron bounces off without leaving a trace in the crystal, a so-called elastic transition. This means the neutron loses no energy and the absolute values of p and p' are the same. This already limits our options for delta p, the change in momentum. And remember, all transitions in the nanoworld must be quantized, so this must also be true for delta p. This is where a second quantum condition comes into play. It involves the crystal symmetry, the directions and distances in which the crystal could be moved and still look the same. The change in momentum must be parallel to one of these vectors di, and their product must be an integer multiple of Planck's constant, which essentially is the quantization of delta p. Putting both conditions together, we can see that for a given initial momentum p, only very special orientations of the crystal can fulfill both conditions simultaneously. Different orientations of the crystal lead to different scattering patterns. By now you're probably asking yourself, what's all the fuss about these patterns? What are they actually good for? As we've seen, the crystal structure and the pattern are connected. So if you measure the scattering pattern, you can deduce the molecular structure of the sample. This is one of the many reasons why neutron scattering is such a valuable method to analyze the structure of matter. It's especially popular in biomolecular research because the neutrons don't destroy organic molecules. And they are able to detect the hydrogen atoms, which are often crucial to the understanding of the molecule's function. In this particular case, Schrader and his colleagues examined beta-lactamase enzymes. These enzymes are produced by bacteria to provide them with resistance against antibiotics. Understanding this process is important for tackling multi-drug resistance of bacteria. And this is just one of many examples of research undertaken at JCNS. In the next episode, we'll take a closer look at the background scattering and take a different instrument for a spin.